Log on, tune in, find out. Another good idea from Cambridge.
Hi everybody, it's a pleasure to introduce our next speaker, Kevin Buzzard. He will explain to us what is an algebraic automorphic form.
Thank you very much for the invite. It's a genuine thanks. I remember coming to the first ever Spitalfields Day, and it was like, people like Ribbit and Mays were speaking, and now me. I'm genuinely flattered. So I'm going to talk about what is an algebraic. I mean, really, I'm going to talk about what is an algebraic automorphic representation. Let me say, I didn't want to give a talk. The title already seemed too long, and this would make it even longer. And also, I was a little bit hesitant because I know what an automorphic form is, but I don't actually know what an automorphic representation is. And I mean, that's in some sense the truth. I'm not sure I could give a rigorous mathematical definition, even though there's plenty of definitions out there. So let me try and really explain in much more concrete terms what this is about. This is a very the bottom line is I want to make a very concrete conjecture about something. So let me start with. I continually want to talk about p-adic numbers being equal to complex numbers. So let me fix once and for all embeddings from Q bar, an algebraic closure of the rationals, into the complexes, and into I want to talk about p-adic numbers. So QP is the p-adic numbers, and QP bar is an algebraic closure of that. And the reason I want to do this is throughout the talk I'll have complex numbers, and I want to talk about them as being p-adic numbers, but the complex numbers will always be algebraic, so they'll live in here, and we'll be able to get down here. That's somehow the preamble. And now, so here's the motivation behind the talk, right? And I mean, I just need to write down I want to write down a theorem that I want to try and generalize, and I've chosen the following result of Deligne. I mean, there's plenty of examples. Let me tell you the following result of Deligne. So here's a theorem of Deligne. So let F be a modular form of some level of level n. So I mean, I'm aware that many of the people in the audience might be interested in algebraic Lie theory or whatever. This is a rather number theoretic statement, but we'll somehow get onto the groups later. So let F be a modular form of level n, and let me assume that F, the sort of standard number theory. I want to assume that F is an eigenform. Assume that F is a normalized cuspidal eigenform. As I say, it doesn't really matter if you barely know what these things are. This is some gadget coming from number theory. So, eigenform for the Hecker operators. So then a construction of Deligne due to many people really, of Eichler. I mean, if I say Eichler and Shimura in the weight 2 case, and Deligne in the weight bigger than 2 case, and Deligne and Serre in the weight 1 case, construction of Eichler, Shimura, Deligne, and Deligne, Serre gives us a representation. It gives us an object which is completely different. I mean, this is a holomorphic function on the upper half plane. Gives us a representation of a Galois group. So it gives us a representation rho from gal Q bar over Q. Let me call this gamma of Q. There's been Galois groups everywhere. So let me just the notation. If I got field of characteristic 0, gamma of that field is just the absolute Galois group of that field. Rho from gal Q bar over Q to GL2 of QP bar. You see, this is the first indicator. This is why I've fixed these things here. F has got complex coefficients but my representation is a p-adic representation. Rho from gal q bar over q to GL2 of qp bar, such that rho is somehow determined by f, such that if L is a prime number, and L doesn't divide n times p, so p is a prime number too, and I'm talking about the p-adic numbers here, and n was the level of the form. If L is a prime number and L doesn't divide np, then rho is unramified at L. Rho is unramified at L, and if rho is unramified at L, that means I can make sense of a Frobenius element, and it means I can make sense of and the char poly of rho of a Frobenius element. I know what it is. It's x squared minus ALX plus L times BL, where AL is the eigenvalue of a Hecker operator, so this is a eigenvalue of the Hecker operator associated with L001, and BL is the eigenvalue associated to the Hecker operator L00L. Right, so let me stop there for a bit. So what is this? This is an amazing thing, right? Because on the one hand, we have an analytic gadget. So, a holomorphic function on the upper half plane with some properties, and it was known for a long time that these had some arithmetic feel to them. But it took until the late 60s before we had the machinery to realize that one way of explaining the arithmetic properties of this thing was that we can attach a Galois representation to an eigenform. So these ALs and BLs will be complex numbers, but they'll be it's sort of standard fact that they're algebraic numbers, and so we can think of them as p-adic numbers. So what I've written makes some sense. So for several reasons, I wanted to generalize this statement to a statement about automorphic representations on a connected reductive group. So let me give a brief reformulation. A modular form can be interpreted as an automorphic form for the group GL2. And the automorphic representation generated by the automorphic form is somehow as good as, knowing F is basically the same as its automorphic representation. So this says, a fancy reformulation of this is if pi is an automorphic representation, so I need to say a couple of things about what such a gadget is, perhaps. If pi is an automorphic representation of the group GL2 over Q, and pi, it turns out, amongst other things, an automorphic representation splits up as a tensor product. This is a representation of a big adelic group, but it splits as a tensor product of pi v, where v is running through the prime numbers union infinity, and pi is the tensor product of pi v. Pi. Obviously, one of these things is different to all the others. Infinity is a rather different kettle of fish to the prime numbers. So let me tell you something about pi infinity. And if pi infinity is a holomorphic discrete series, whatever that means, I don't know actually. It's a holomorphic discrete series representation of GL2R. I should say that pi p is a representation of GL2 QP, and pi infinity is a representation of GL2R. And some representations of GL2R are called holomorphic discrete series. These are infinite dimensional Hilbert space representations. So this is quite a fancy, complicated object. Blah, 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 blah. Then, so I'm trying to reformulate what Deligne did. Then attached to pi, then there exists some rho equals rho of pi, kind of attached to pi. So rho is just this representation. I'm not going to write that again. Rho is the same thing, the same map from the same spaces, such that rho rho locally at L is determined by pi locally at L. Well, it's determined by pi L if L is a prime number. So the sort of standard convention in this game is that prime numbers are L and P, but V is either a prime number or an infinite place of the number field. That's a fancy way of saying it, which in this case is Q. So normally you see Deline's theorem stated in this way, but there's actually this is an automorphic reformulation. So I don't really want to go into what automorphic representations are, but if you haven't got a clue, so for example, if you're me about 2 years ago, then you just need to know that an automorphic representation is a huge amount of data. It's representation. So this pi v is pi p is a representation of GL2QP, and pi infinity is a representation of GL2R. And more generally, for a general connected reductive group over a number field, things will break up in this way. So pi is some huge tensor product of representations of reductive groups over local fields. And there's this amazing result of Deline that says in this one case, GL2 over Q, attached to this analytic object is a very algebraic object. And I could have done something else. Instead, I could have stated, there's a much older result of Vey that says for an automorphic representation for the group GL1 over a number field, there are associated one-dimensional Galois representations. So that would be another way of motivating what I'm about to say. I'm about to write something on this board which will somehow stay there for a while. So that the big question is what's the general conjecture about? So I want to write I want to find a general conjecture for which this is a special case. But before I start attempting to formulate one on this board, I'll maybe make some comments that you would imagine that the Langlands philosophy is exactly, or this aspect, there is an aspect of the Langlands philosophy which is exactly associating representations of Galois-like groups to representations of reductive groups. And so one can look at the Langlands philosophy and see exactly what it says, but it doesn't, as far as I know anyway, the Langlands philosophy doesn't predict this theorem of Deline that's on the board in some sense. The Langlands philosophy says that given pi, I don't need any condition at all about what's going on at infinity, and attached to pi, there should be a two-dimensional representation of a complex of a Langlands group, which is some group that nobody can really define. But the idea is that there should be a category of automorphic representations, and it should be a Tanarchian category. So it should be the category of representations of a group. But no one knows what. It's certainly not this Galois group. It's much bigger than this Galois group. So there's a very vague. There's a very vague philosophy as to what a general conjecture should look like. But it's not about p-adic representations of Galois groups. It's about complex representations of groups that aren't known to exist. So for me, that's kind of unsatisfactory. So I wanted to see what the general conjecture was, which implies this theorem of Deline and the theorem of Vey that I mentioned. So let me write sort of a conjecture. And it needs to be in quotes because as what I'm going to write somehow is not going to be very well defined, right? Conjecture. So, and as the talk goes on, the conjecture will become more and more refined until hopefully at some point it will make sense. But that won't be the end of the story. So if G is a connected reductive group over a number field, let's call it F, and pi is the tensor product of pi v, is an automorphic representation of G, then I'll explain a bit more carefully later what these things look like at least. So those of you that have no idea what such a thing is, at least will kind of see. They won't know the definition, but you'll know the basic properties somehow. I've got a connected reductive group over a number field, and I've got an automorphic representation of G over F. So now what's the analog? I need some assumption about. I need some assumption. You see, this statement wouldn't be true for a random automorphic representation of GL2 over Q. The the Hecker eigenvalues would be random complex numbers that probably wouldn't be algebraic at all. So we need some kind of algebraicity statement, and if pi, and so this is the first thing that goes in quotes, if pi is algebraic, so that's a missing definition that will perhaps come later. If pi is algebraic, that's in quotes because that doesn't make sense yet, and the conjecture doesn't make sense. If pi is algebraic, then there's going to exist some rho is rho pi, and it's going to go from, I've got a connected directed group over a number field, so it's going to go from gal f bar over f, gamma of f, I call that, didn't I? Gamma of f to, what did I go before? GL2, I mean, to some p-adic group. So that needs to be fixed as well, such that what's going on locally at rho is determined by what's going on locally at pi, such that if V is a good, if V is an unramified prime, unramified for everything, if V is a good prime in some vague sense, and V doesn't divide P, then, so the last thing I'm going to put in quotes, even though many people in the audience will know full well how to make this, how to formulate this rigorously, then rho is unramified at V, and furthermore, rho of a Frobenius at V equals something to do with some formula depending on pi. Some formula depending on pi v. There. So this is the starting point of my talk, and I hope to kind of plod quite slowly, but somehow I have to start somewhere, and I've decided to start here, assuming a certain amount of machinery. So this is in quotes as well. So why was I interested in this? Why was I interested in reformulating this fancy conjecture of Deligne? Well, actually, what I was interested in was working out what it means for an automorphic representation to be algebraic, because I have this vague picture in my head that, there are these definitions. There's a classical definition of an automorphic form. Here's a vague picture. We've got G a connected reductive group, and then we've got this definition of automorphic representations here, which, as I say, I still haven't really ever got to the bottom of. But living in there, we have the kind of algebraic automorphic representations there. And my belief, somehow, from thinking about very trivial cases, like the case of GL1, is that over here there should be some p-adic automorphic representations there. So here, I'm just sort of muttering that I don't really quite know the definition because I don't really understand Hilbert space direct sums very well. And here maybe we have some ideas, but here no one knows. No one knows what a p-adic automorphic representation is. I mean, for specific groups, there have been kind of specific examples suggested. But at the minute, we're really missing. This definition is not. We haven't come to. Today I can tell you what this will be. This has been known for years, but nobody quite knows what this is. But my hope was we could somehow get some insight as to what this is, because people are trying to formulate p-adic Langlands philosophies and things like this. And 10 years ago, that would have sounded a bit pretentious somehow. But nowadays, people have really proved non-trivial theorems that can somehow be interpreted as p-adic local Langlands conjectures for GL2 over QP and things. There's clearly something going on here, and maybe mathematics is just about ready. But this is my hope as to what the link would be between a classical story and a kind of a new, yet to be formulated story. This would somehow be the link that joins the two. So I knew nothing about automorphic representations a year or so ago, so I thought I should try and at least learn enough to work out what an algebraic automorphic representation is. And then a student, Toby G, who independently wanted to know what an algebraic automorphic representation was, because Toby G, he wanted to prove a kind of Sayre. He got very interested in Sayre's conjecture. Somehow he got very interested in going the other way. So you had a mod P representation of a Galois group. When should it be attached to an automorphic representation? And I mean, Toby proved some non-trivial things. He proved lots of cases of a conjecture I've made with Fred Diamond and Fraser Jarvis for the group GL2. And he wanted to push this as far as it could go. But for some technical reason, he absolutely wanted to work with a general connected reductive group. So he wanted to know what the correct formulation of a conjecture was, so he could then attempt to go and try and prove it, or try and prove some things about it. So I thought this was as good a motivation. I figured I'd try and formulate it, right? Because I thought that would teach me some basics of the theory, and then I'd get the hang of it. So that was that picture was in my mind a long time ago, but somehow removing all the quotations and getting something. It sounded like a basic task. Something that you could ask an expert and they'd tell you, but why not work it out for ourselves? So that's what we decided to do. And if we'd just kind of done it, and it just was a case of looking up the definitions, and we got a satisfactory answer very quickly, then I probably wouldn't even give this talk. It would somehow be too uninteresting. But we ran into a couple of funny things on the way, so I thought I'd mention the funny things, because they somehow seemed worth highlighting. So maybe I should say that for the group GLN over a number field, there is a well-formulated conjecture, and it's due to close L. But he assumed that, I don't know, there's a conjecture due to close L, and if G is kind of semi-simple and simply connected, then there's some. If G is semi-simple and simply connected, and say G of R is compact or something, then probably all pi's should be algebraic, and there's a conjecture of Dick Gross that makes this rigorous. But for some reason, these weren't enough for Toby G, who's definitely worth a mention. This is so. From now on, everything I say is kind of joint work with Toby G, who's currently a Ben Pierce at Harvard, doing very well for himself. So we had this rather trivial problem, and these were our thoughts on it. So the first thing I'll do is I'll tell you what the answer is down here. This is a very standard thing. It's been known since at least the 70s, probably much earlier. So here's the story of the good primes. So here's the story of the good primes. So as I say, I don't want to get too bogged down in what an automorphic representation is, but if pi is an automorphic representation, so an automorphic representation of the connected reductive group G over a number field F. Did I say that F was a number field? I must have done, yes. Then pi, then here's the first thing you really need to know about pi. Then pi is this tensor product of pi v, where v is now running through the primes of F. V is the primes of F union the infinite places, which is basically the maps from F to the complexes, modulo a map is equal to its complex conjugate. And pi v is a representation of the group G of Fv, where Fv is the completion of F at V. Sorry, Fv is the completion of F at V. So I'm interested in the finite primes at the minute, so I'm not going to write Fv all the way through. Let's introduce some new notation. So now let K be a finite extension of the group of QL there for L a prime number. So these are this is the p-adic numbers P, but I want to use L because I've used P for something else. So let K be a finite extension of QL, and say G over K is connected reductive. I've got a connected reductive group over a p-adic field, over an L-adic field. And let's say pi. Now pi, I really should write pi v or something, but I'm not going to bother because I know I'm in the local situation. Let's say pi is a smooth, irreducible. Smooth just means basically continuous. So there's a smooth, irreducible representation of g of k there. So now, so it turns out there's a notion of, there's a good notion of being unramified. Let's assume pi is unramified. So there's some technical definition, but let me just tell you that the thing you want to be true is true, which is that if I have an automorphic representation, so back to the global setting, then it's unramified outside a finite set. So assume pi is unramified, which, as I say, will be true for almost all but finitely many v's. So this means, so the correct definition of unramified means, i.e. there is a fancy thing called a hyperspecial maximal compact subgroup, capital K. Now I'm hoping I haven't used capital K for anything. That was my plan. I think I've got away with it. Some hyperspecial maximal compact K living in G of little k. Because capital K is a good name for a compact subgroup. There's a hyperspecial maximal compact subgroup K such that pi has a K fixed vector. Such that pi is now a representation of this huge group G of k, but there's a big compact subgroup such that pi k isn't 0. So in this case, so pi, sort of terminology, pi unramified implies G unramified, so in case anyone's wondering. So in this case, pi k is one-dimensional, and although, of course, the group G of k doesn't act on, G of k acts on the vector space underlying pi, which I'm also calling pi, but this group G of k doesn't act on the k fixed vectors because G of k won't normalize the compact in general. But in this case, pi of k is isomorphic to C, but instead of the group acting, we have a Hecker algebra acting, and hence gives a one-dimensional, well, gives a character of the algebra HC of G K. I'll write it like that. So that means locally constant functions on this p-adic group G of K with compact support, and which are furthermore by K invariant. So that's a Hecker algebra. So locally constant, complex valued. That's what this C is. This is locally constant functions with compact support. So now I've got an unramified representation of this group G of K. So pi of K is now a representation of this. Turns out to be commutative. It's not immediately obvious. This is a commutative ring with a 1. I need to give you a multiplication on the locally constant function with the compact support. I'll do convolution. Convolution is the multiplication. And I need to tell you what Haar measure is if you want to convolute things. So I'll choose a Haar measure such that the measure of this compact open is 1. So now the characteristic function of this compact open is an identity. So this is a commutative ring with a 1. It's a C algebra. Its structure is very well known, and I get a representation of that. Well, that's not great. Yeah, what I'm trying to get is I'm trying to get some conjugacy class, right? I'm trying to get a conjugacy class in a group because I'm trying to remove these quotes. So the next thing we observe is that the structure of this unramified Hecker algebra is very well known via the Satake isomorphism. So there's a completely canonical, so there exists a canonical isomorphism from this Hecker algebra I've just written, G of K. It's isomorphic to, I'm going to write equals because it really is a canonical thing, is HC of T of K modulo compact open, modulo, I'll have to call it KT, fixed by W, where T of K T, so I mean, T is a T lives in a Borel, lives in G. So this is a Borel. This is a Borel subgroup, and this is a maximal torus. Maximal torus was in the Borel. So these are somehow, this is the standard buzz phrase, and I'm not going to get into all of this. So T is a maximal, I mean, if G is GLN, then this overall says this, it's a useless thing to say. If G is GLN, then B is the upper triangular matrices, and T is the diagonal matrices. So T is some torus, and then W is some Weyl group. But when I was a graduate student, I saw this explicitly explained for GL2, and somehow if you know that, and then K of T is the unique maximal compact subgroup of T of K. So the canonical isomorphism from here to here, and this is just the same. This is another Hecker algebra, continuous complex valued functions with compact support on this L-adic group, which are by KT invariant. But we've got a character of this commutative ring now, still not a conjugacy class somehow, but what we can do is we can now invoke some old results of Langlands and Gantmacher, which tell us that to give a character of this gadget here, and hence pi, and so pi. So pi gives us a character of this thing here, HC T of K, W, and hence by a general machine, which I won't go into, and hence a semi-simple conjugacy class in the L group of G. There. So this is, as I say, from standard results from decades ago, and I'll remark that if G is GL2, then all I've said is some very, very fancy. When you translate this very, very fancy thing down, you get. So I haven't even told you what an L group is. So the L group of G is some extension. I mean, it's a semi-direct product of the dual group of G with a finite, I mean, gal K1 over K, where K1 is some extension of K that splits this group, and this is the dual group. So if you know what if you know anything about connected reductive groups, you'll know that you can attach some combinatorial data to them. G contains some torus, and you'll work over an algebraically closed field, and G will have some torus, and G is basically determined by the character group of the torus, the co-character group of the torus, and some finite amount of data, the roots and the co-roots. G is determined up to isomorphism by this. But once you have this algebraic data, you can swap it round. The roots of G are the co-roots of some other group, G dual, and the character group of G is the co-character group of some other group, G dual. So rather than give you a rigorous definition, let me give you some kind of table. If G is, if G is G, what's G dual? So if G is GLN, then G dual is GLN. Normally people work over the complexes, but let me let the dual group be an algebraic group over Q bar. But if this is SLN, then you get PGLN. And if this is PGLN, then you get SLN. It's interchanging the adjoint and the simply connected. I'm assuming a huge amount of stuff which is very well known to some people, but it wasn't known to me until a couple of years ago. But at the end of the day, this local story is very well understood, and there's some group called the L group, which is a bit like a Galois group product, some kind of complex Lie group, and the local story is giving us semi-simple conjugacy classes in some L group. So now it's kind of clear what should be going on here. I want to rub out some p-adic group, and I want to replace it with the L group, LG QP bar, there, such that then rho is unramified at V, and rho of frob B, is the semi-simple conjugacy class attached to pi v. So we've still very much got a conjecture in quotes, but this is the local part of the story, and this is a very standard thing. So that's probably what our conjecture is going to look like. So now let me raise a little bit of a worry in that this genuinely is the complex numbers. The story that pi is a complex representation, and this yoga gives you some complex conjugacy class in here of elements with complex numbers in, and I want to talk about them as being p-adic numbers. So it wouldn't be very good if they were transcendental, because then somehow I don't really want to fix an isomorphism of C with QP bar, because that seems a bit pathological. It would be really good. I need really my semi-simple conjugacy class had better be in Q bar, right? That's what I'm after, because if it's in Q bar, then I fixed very analogous to this picture. I fixed some Q bar into C and into QP bar. So this algebraicity condition had better imply that certain eigenvalues are algebraic numbers. That's like the following statement. If you have a modular form, which is a complex analytic function on the upper half plane, then the Hecker eigenvalues associated with that form would better be algebraic numbers, right? That's a true statement, but in this generality, it's going to be a conjecture. I mean, we could either build it into the definition of algebraic, but I want algebraic to be a condition of what's happening at infinity. So there's an arithmetic condition going on here. So this is hopeless. This is never going to be true unless algebraic somehow implies arithmetic. So I need to work out a good notion of arithmetic to make sure that somehow my conjugacy class is defined over some number field, really. I don't even really want Q bar. I really want everything. I mean, the coefficient of a modular form generates a number field. I'd like to have a number field going on here. So let me tell you two definitions of arithmeticity. And the funny thing is that they're different. So we didn't quite know which one to use at first, but here's two natural notions of arithmeticity. So recall, so we have pi, we have an unramified pi, so a representation of GK. And as I sketched, pi gives rise to two representations. So it gives rise to a ring homomorphism from HC of GK, K to C, and it gives rise to a ring homomorphism. I'm just going to write the same group again. I'm going to write it in this other form, HC of T of K modulo KT to C. So there's two perfectly, I mean, these rings are isomorphic. So we have these two ring homomorphisms. And these rings also both have very natural Q structures. So we could replace C by Q. So we could say, here's a definition. So if E lives in C, it's a subfield. I mean, it's definitions, right? Let's say pi is defined over E. If the image of H, I'll change those C's to Q's. HQ of GK over K lives in C, lands in E. Well, if the image of this thing here lives in E. So this is locally constant functions with compact support, but taking values in the rational numbers. So that's now a commutative Q algebra. That's a finally generated Q algebra. But we've got this other Q structure as well. We've got two very natural Q structures on these finitely generated C algebras. One coming from, one coming from the group G and one coming from the torus. So two, let's say pi has Satake parameter defined over E. Again, a subfield of C if the image of a HQ T of K over KT lives in E. So as I say, I was just trying to learn all this stuff, and it wasn't quite clear what notion of arithmeticity I wanted, so we had to kind of work out what these said we had to work out some examples. We had to try and work out what was going on. So let me just pause for a second and give you some kind of concrete examples. So, examples. So let's have, what about the trivial one-dimensional representation of GL2QP? So GL2QP acts trivial on a one-dimensional vector space. So that's unramified. GL2ZP is a perfectly good hyperspecial maximal compact. And then the Hecker algebra acts on the complex numbers, and obviously it's somehow acting in some completely trivial way. So the trivial one-dimensional representation of GL2QP is defined over Q. In fact, I could have given you an equivalent definition of being defined over E is that here's it turns out to be equivalent to 1, that there exists some pi 0, an E vector space, plus a GK action, such that pi is pi 0 tensor C over E. Nobody can probably read that, but pi being defined over E is really, in the sense of representation theory, it can be realized. It can be realized over an E vector space. That's all that this one means. So obviously the trivial one-dimensional representation, we can realize it over Q is defined over Q. But when you unravel the definitions, the Satake parameter, the semi-simple conjugacy class, turns out to be root P. I mean, ever since I was a graduate student, I've seen these stupid square roots, 1 over root P. So I realized I was going to have to keep my head somehow. So it's not defined over Q. So it's defined over QP, defined over Q root P. I can hear mutterings. Is everything all right? I don't know. Is this what's normalized right? Is this one normalized right, or is this one normalized right? I'm not entirely sure, right? Because if I want to transfer from C to QP bar, I want the Satake parameter to be defined over Q. And this one isn't somehow. If I consider the trivial one-dimensional representation of GL2 of the Adels, the Satake parameters of different primes will be defined over different number fields. It sounds a bit scarier. So another example would be, that's example 1. Example 2, I could twist it. Let's consider the representation still of GL2QP. Consider the determinant, that's a map to QP star. Consider its norm, that's a map to the positive reals, and take its square root. There, that's a representation of GL2QP. Rep of GL2QP. There. So the Satake parameter is P001. So the Satake parameter is defined over Q, but pi is defined over Q root P. Because the norm, P001 has determinant P, the norm of P is P, the square root of P is root P, so you've got some action involving some square root. So these are different notions of being arithmetic. So I've got this muddled idea that we want to formulate something like this. So, yeah, I don't quite know which is the right notion yet. Well, I couldn't decide which one to choose, so eventually I chose both of them. And I decided that there was more than one notion of being arithmetic in the theory of reductive groups. So maybe I should say that this is where I diverge with people like Dick Gross and Clausel. They're aware that there's more than one notion, so they'll put themselves in a situation where the notions are the same. So Dick would assume that G was kind of semi-simple and simply connected. So then the notions turn out to coincide, because the issue is half the sum of the positive roots. Half the sum of the positive roots is not a weight for GL2. So Dick assumes that half the sum of the positive roots is a weight, and the problem goes away. Clausel knows that for GLN, half the sum of the positive roots isn't a weight, but he just they're only out by some twist. So he'll renormalize everything in terms of a twist. And he has a funny normalization of the Satake isomorphism in his paper. And we didn't really want to do that either, because we knew examples of groups G where you couldn't fix things up by twisting. So here's global definitions. So 1, let's say an automorphic representation pi for a connected reductive group G is, well, Langlands likes his Satake parameters. Langlands functoriality works very well with, Langlands functoriality obeys the Satake formalism. So I'm going to say, instead of calling it arithmetic, I'm going to call it L-arithmetic, if there exists some number field E. E living in C has to be a number field now, finite over Q, such that pi v has Satake parameter defined over E for almost all v. That seemed to me to be a very natural notion of arithmetic. So an example of that for the group GL2 would be so GL2 of the adels of Q, just take the determinant AQ star, take the norm to the positive reals, take the square root goes to the positive reals. That would be L arithmetic. And the Satake parameters attached to a prime P would be P001, and the Galois representation is going to be trivial plus cyclotomic, right? So that's a good thing, L arithmetic. And then, of course, 2, we need to do the other notion. So pi is, well, I'm going to put C arithmetic. For C is a good letter for 2 reasons. Firstly, because Clausel defines a notion of arithmetic in his paper, which is going to coincide with this, but also because cohomological representations are being realized in the Étale cohomology of Shimura varieties. So they're going to be defined over subspace. They're going to be defined over coefficient fields in this sense here. So cohomological representations seem to be defined over E in this sense. So it's C arithmetic if pi v is defined over E as above. So E a number field. You know, if there exists some number field E as above, such that pi v is defined over E for almost all v. Wonderful. So at the minute we're kind of stuck. We don't know what the right definition is. Well, so then we take the trouble to read some of the literature. And there's this paper by, well, Harris, Taylor, Shepard-Barron, and Clausel have written a bunch of papers. I mean, various subsets of those people have written various papers over the last few years where they prove a theorem. I forget making conjectures. They prove a theorem. If pi is an automorphic representation over a unitary group, then they really attach a Galois representation. So it's like, great. That's another clue, right? Let's just unravel what's going on, and we'll try and work out what this definition. I mean, maybe cohomological. Maybe we should write cohomological. I don't know. So these people, given a cohomological automorphic representation, they attach an explicit Galois representation to it that's taking values in some group that's a semi-direct product of a reductive group and a Galois group. And you think, brilliant, that just must be the L group of the unitary group. So we then unraveled that they have this G is a unitary group. They have a theorem that attaches a Galois representation to something. So we compute the L group of their unitary group, and it's not this, which surprised us. So I emailed Taylor and said, do you know, you've attached a Galois representation to a group that isn't an L group. So what is it? Because I'm trying to figure out what's going on. He said, I don't know. He said it was the group that came out in the wash. So he said, maybe it's the L group of the general unitary group. So we computed what the L group of the general unitary group was, and it wasn't it either. So suddenly we've run into an obstacle. So after a bit of confusion, thinking, are we actually doing the right thing, I realized that there was actually a much more trivial obstacle. Here's a trivial obstacle to formulating this conjecture. So here's an obstacle that we somehow have to really think about now. Say E over Q is an elliptic curve. In the old days, I would have said a modular elliptic curve, because that's the thing I need about it. But they're all modular now, so let's say pi is the associated automorphic representation of GL2 over Q. There's a normalization issue. You have to decide what the central character will be. So let's just normalize it in the standard way. So normalized such that the central character is trivial. This is the standard normalization. For higher weight modular forms, there's more than one standard normalization, but for elliptic curves, this is the standard thing. So I've got a representation of GL2, which is trivial on the center, so it descends to a representation of PGL2. So pi is now a representation of PGL2 over Q, an automorphic representation of PGL2, and it's visibly algebraic, right? It's come from an algebraic gadget. Pi is clearly going to be algebraic. So pi is clearly algebraic, in the sense that any conjecture that ends up with a notion of algebraic for which this isn't algebraic, one has to really start wondering whether it's the sensible conjecture to make. So our conjecture, great, so what's the state of our conjecture? It's still a bit vague, but attached to pi, what does our conjecture say? So pi is algebraic, so we're over that hump, and then there's no more quotations left, is there? Wonderful, so pi is visibly algebraic, and attached to pi, there should be a representation to the L group of PGL2, so hence attached to pi, we're going to predict, our conjecture predicts some representation rho from gal q bar over q to SL2 of QP bar, SL2 being the L group of PGL2. Now this is a big problem because there is clearly a representation attached to pi, and it's clearly the Tate module of the curve, right? So the truth, this is rubbish, right? So the truth is that the Tate module of E is from gal q bar over q to GL2 of QP bar, and determinant is the cyclotomic character. And we're going to need to twist, right? We need to twist to get it from GL2 to SL2, but you can't. You can't twist because we need to twist by a character whose square is the cyclotomic character. Sorry, I shouldn't put that square root there. The character we need to twist by is a character whose square is the cyclotomic character. And the cyclotomic character, when you evaluate it at complex conjugation, it's -1. So its square root is going to be a character of a group that sends an element of order 2 to an element of order 4. And that's not so great. The cyclotomic character has no square root, so we can't twist this to get in here. So suddenly, it's fallen through, the whole thing's falling about our ears. And so we were forced to make some disturbing decisions, and the disturbing decision was that this visibly algebraic gadget is not algebraic, but pi is not algebraic. Which is a big problem because that makes our conjecture rubbish, you see. I mean, maybe we're going to come up with a conjecture, but if it's not going to attach the Tate module of an elliptic curve to our Gauss representation, then it's going to be useless because what we wanted to do is our goal at the beginning was to kind of formulate a general conjecture that implied every instance of a conjecture and a theorem in the literature where G was some special case, right? If G was abelian, there are theorems of Weil. If G is GLN over a field and pi is self-dual, there are theorems of Clausel. For unitary groups, there's all sorts of theorems nowadays. There's theorems of Weishauer and Taylor for symplectic groups. There's GL2 over imaginary quadratic fields. There's conjectures of Gross for semi-simple, simply connected groups. We wanted to write down a general conjecture that implied all of them, and suddenly it's not even going to do the most basic thing. So now we had to do some unraveling, and our unraveling made it quite clear what the conjecture should be. So here's the conjecture in its, well, not the current form because there's a punchline. So here's definitions at infinity, finally. Now let's say K is isomorphic to the reals or the complexes. And let's have G, a G connected reductive over K. Because now you see, I've been very vague about what the good notion of arithmetic is, but now I want to tell you what the correct, what our notions of algebra. So now I don't know anything about representations of Lie groups, but I've got to bite the bullet and find out. Let's say pi is a representation of G g of k, well, what data can we attach to pi? So attached to pi, I mean the infinitesimal character of pi, when you unraveled it, when unraveled, is an element via the Harish-Chandra isomorphism, which is an Archimedean analog of the Satake isomorphism, is an element of, let's just say, I'm being a bit vague because I want to finish up. Is an element of x, is x star t tensor c. It's not quite that, though, because there's a Weyl group orbit again. So it's a W orbit, is a Weyl group orbit in this. There. And now, to our glee, we found out that although we couldn't quite decide what to do in the arithmetic case, we also couldn't decide what to do in this case as well. So there's a very, very natural definition of algebraic. So let's say, I've got a lattice, and I've tensored it with C, and I've got a W orbit, where W is the Weyl group. So we wanted to define algebraic to mean that the orbit's actually in x star of t. So let's say pi is, and this is, Langland's normalizations of everything work very well with the Harish-Chandra isomorphism normalized in the correct way. So let's say pi is L algebraic, L for Langland's again, if this parameter, let's say is an element lambda in this. It's strictly speaking, it's a bit more complicated than this because I need to choose an isomorphism of k bar with C, and I can choose two isomorphisms and get two different lambdas. But everything I say turns out to be well-defined independent of choices. So let's say, well-defined, well-defined up to W. Its W orbit is well-defined. So let's say pi is L algebraic if lambda's in this T. So if G of R is compact, then this representation will be finite dimensional. And when you normalize the Harish-Chandra isomorphism in the right way, it involves half the sum of the positive roots again. So finite dimensional representations typically won't be L algebraic. So, because there's a half the sum of the positive roots issue. So let's say pi is C algebraic. If lambda minus half the sum of the positive roots is an x star of t. So two very natural definitions of algebraic that we couldn't choose between, but of course the notation tells you what's coming. So here's the big conjectures then. Conjectures. So conjecture L1 is that pi is L algebraic if and only if pi is L arithmetic. And conjecture C1 is that pi is C algebraic if and only if pi is C arithmetic. So for the group GLN, Clozel conjecture that arithmetic if and only if algebraic. And Clozel's conjecture was this. For GLN, these conjectures are equivalent because if you're C arithmetic, then some twist is L arithmetic. And these notions are equal up to a non-trivial twist. And if n is odd, if n is odd, these notions are disjoint, but somehow one can be twisted into another. For a group like PGLN, these notions are completely distinct. For PGL2, this is two completely distinct conjectures with essentially no relation. And so now we make conjecture L2. If G is a connected directed group over a number field, and pi is an automorphic representation, and remove the quotes finally, everything's normalized. The L stuff was when the Satake parameters were defined over a number field, so the only thing you can write here, if pi is L algebraic, that should be the conjecture. There's conjecture L2. So I've got an L conjectures 1 and 2, and C conjectures 1 and 2. So there's so for GLN, that specializes to something which isn't, something which is trivially equivalent to what Clozel conjectured. But unfortunately, there's no conjecture C2 on the board. And that's bad because the kind of when could you hope to prove something you've got an automorphic representation, when can you hope to attach any kind of Galois object to it? When it's cohomological. When G has Shimura varieties, and if pi is cohomological, then you can attempt to realize rho within the cohomology of a Shimura variety. And cohomological representations are going to be C-algebraic. And they're not L-algebraic. And so Clausel gets around this by renormalizing local Langlands, but you can't do that in general. So we were kind of thinking that must be the conjecture, but it's a bit rubbish because it doesn't say anything. I mean, we don't recover. I mean, the problem. I'm rubbing off the problem. The problem was, somehow. So I'll finish this board, then I'll stop. So problem, naturally occurring. So many naturally occurring pi are C-algebraic and not L-algebraic. There's no reason they should be L-algebraic. If half the sum of the positive roots is a weight, then these notions all coincide, and we have a conjecture. So e.g. for PGL2, we do not have a conjecture about the representation attached to a modular form, and indeed we shouldn't have, because the representation attached to a modular form doesn't land in SL2, whereas the automorphic form does descend to PGL2, but we fixed it. Over the moon with this fix, and I thought I've overrun, but somehow I thought I should tell the world what the fix is. Here's the fix. So as I told you that for GLN, we're okay. For GLN, C-algebraic representations are commonplace, but you can twist them by some, by this, determinant to the half. If you twist by determinant to the half, then C-algebraic representations for GL2 become L-algebraic and vice versa. So for a general group G, we can't twist. This was the problem. So let's say G connected reductive. There's a central extension of a central extension. Is that a central extension? I don't know. I'm so naive at this sort of thing. There's a central extension of a central extension of G, which is also connected reductive, let's call it G tilde, such that on G tilde we have enough space, such that G tilde of the Adels admits a character that twisting all our C notions into the L notions. So conjecture C2, which I don't have the time to write down. You see, now the idea is you take your connected reductive group like PGL2, you take your C algebraic automorphic representation, like the one attached to a modular form. You can't twist it to make it L algebraic, but there is some cover of G. Surprise, surprise, it's GL2 in this case, when you unravel our recipe, such that on GL2, it admits a character such that if pi is C algebraic, so pi C algebraic, if and only if pi tends to this character is L algebraic. So given an automorphic representation for G, we lift it to an automorphic representation of G tilde. We twist it, so this lifted thing is L algebraic. We can now apply this conjecture. So we get so the C conjecture is, so pi gives a representation to the L group of G tilde, QP bar, which is only well defined. I mean, you have to carry the twist around. So when you unravel this for the group PGL2, it says, given the representation attached to a modular form, you shouldn't get a representation to the L group of PGL2, which is SL2. You should get the representation to the L group of the cover, which is GL2. So modular form should give you representations to GL2. And then, of course, the punchline is we stared at Taylor's result. We took our unitary group. We figured out what the central extension was. It wasn't the general unitary group. It was some funny group G tilde. We computed the L group of G tilde, and it was what Taylor et al. Had predicted. So we finally got our conjecture that somehow, as far as we can see, implies everything in the literature. And I'm done, and I'm sorry for overrunning.
Thank you very much. Are there questions, comments?
Can one say what G tilde is? And you didn't tell us what G tilde
Oh, I see. So first of all, you make it as first you make a random. First you make a central extension that makes the derived subgroup simply connected. And then you make an extension by GM. So what you need, this character. So you want G goes to some S, the maximal split quotient torus, and the character group of S lives in the character group of T, which is just a maximal torus of G, and it's exactly X star is where the Wahl group is trivial and the Galois group acts trivially. So I need to find some. So the upshot is to find this chi. I need to find something. I need to find some theta in X star of T, such that firstly theta is W invariant and Galois invariant. And secondly, I need to make sure that theta pairs with alpha. So for an arbitrary simple co-root, alpha dual, theta pairs with it to give the number 1. If you have such a gadget, then you see half the sum of the positive roots is a very good candidate because it satisfies all these properties, but unfortunately it might not be in here. So half the sum of the positive roots would do. So for GL2, half the sum of the positive roots won't do because that's kind of a half, negative a half. But of course 1, 0 will do because there's, this is somehow, no, yeah, no, it won't do. I need half the sum of the positive, well, no, I've got something wrong. What do I need? Maybe I don't need to be W invariant. I need to make, the idea is I need to make sure that theta minus delta, I need to make sure that theta minus delta is W invariant and G invariant. So I need to find some G invariant thing that pairs with one with every, that sounds right to me. And so if such a gadget doesn't exist in my torus, then I simply make I bump up the torus by some central extension by inserting an element that has the properties I require of it. So going to the first central extension is just some trick because it's nice to have simply connected derived subgroups. But then the second central extension is explicitly inserting an element of the character group which isn't there. If it's not there, then I'll insert it. And that involves adding a GN. And when you unravel it, I've explained that very badly. I'm sorry, I didn't prepare that very well. But I had it written down. I can tell you what. But that's the idea. You need an element of your character. You need half the sum of the positive roots to be a weight. And if it isn't, then you insert another thing that might not be half the sum of the positive roots, but has all the properties of half the sum of the positive roots that you need on it. That's the answer.
Okay, let's thank the speaker again.